In 1913, inventor Nikola Tesla created a turbine that he claimed had an efficiency of up to 95%. However, the world eventually forgot about it. Was this invention as great as people rumored, or was there a conspiracy preventing the widespread adoption of the Tesla turbine? We will uncover the truth in this video. A turbine is any rotating mechanical device that extracts energy from a flow of liquid or gas and converts it into useful work. Water wheels, mill wheels, or water wheels are among the simplest and most intuitive examples of a turbine. They harness the natural flow of rivers and streams to rotate a wheel with multiple blades or water scoops attached around the outer rim. The water wheel is mounted on a horizontal shaft, and as the wheel moves, the shaft rotates, generating power used for milling rice, grinding corn, or operating hammers to forge weapons and farm tools. Water turbines were developed in the 19th century and were widely used for industrial production before electrical grids existed. Today, they are primarily used for power generation. In hydroelectric dams, water from reservoirs is directed through a system of pipes, spinning the blades of a turbine. This turbine, in turn, rotates a generator to produce electricity. In thermal and nuclear power plants, turbines are driven by high-pressure steam, while in wind farms, turbines are powered by the wind. These are respectively called steam turbines and wind turbines. Despite their differences in type, all turbines operate on the same principle, using blades to capture the flow of water, high-pressure steam, or air, converting kinetic and potential energy from the fluid. Fluids, which include both liquids and gases, cause the turbine blades to move, transferring rotational energy to the rotor. It is evident that one of the most crucial components of a turbine is its blades. The blades of modern turbines, especially steam turbines, have highly complex designs, requiring extremely advanced manufacturing techniques. The average blade diameter of a modern wind turbine reaches up to 127.5 meters, longer than a football field. High-speed fluid flow enters one end of the turbine and exits at the other end at a lower speed. The energy from this change in speed is what drives the rotation of the blades. During this process, a certain amount of energy is lost. Modern multi-stage blade turbines can typically harness only 60 to 70% of the potential and kinetic energy of the fluid flow. However, large steam turbines and hydro turbines, especially those used in power plants, can achieve efficiencies of over 90%. Let's take a closer look at a hydro turbine. When water enters the turbine, chaotic vortices form inside. These vortices move in various directions, and instead of efficiently spinning the blades, they create friction with each other or against the turbine walls, generating heat and causing energy loss. The same phenomenon occurs when you pour water into a blender. Tesla observed that in traditional steam turbines, steam must be forced against the blades for the rotor to extract energy from the steam's velocity. Under optimal operating conditions, the blades must be arranged to minimize the angle at which steam contacts their surfaces. The goal is to create a smooth steam flow and avoid turbulent currents. Turbulent steam flows are problematic because they waste useful energy that could otherwise be extracted from the system. Even worse, a chaotic reverse-flowing steam current can reduce the kinetic energy of the smooth incoming steam flow. What you're looking at is the design of the Tesla turbine, patented in 1913. Tesla solved the problem of turbulent flow by inventing a bladeless turbine. Instead of blades, the Tesla turbine uses rotating discs. This design minimizes resistance, allowing fluid flows to follow their natural paths. Essentially, the Tesla turbine consists of a set of smooth discs with fluid nozzles directing flow toward the edges of the discs. As the fluid is pumped into the turbine, it drags the discs along due to viscosity and surface adhesion. After transferring part of its energy, the fluid slows down and exits through exhaust ports near the center of the discs. The driving force behind the Tesla turbine is a fascinating and somewhat mind-bending phenomenon known as the no-slip condition, also referred to as the no-slip boundary condition. Now, let's observe the following experiment. A dark-colored dye is injected into the bottom of a flowing water stream through a glass tube. While most of the dye gets carried away by the current, a small amount remains stationary, forming a thin layer near the bottom of the water flow. That is precisely the no-slip condition in action. Let's break it down. When a fluid flows very close to a solid surface, the attractive forces between fluid molecules and solid molecules are stronger than the forces between the fluid molecules themselves. This causes the fluid layer to stick to the solid surface. As a result, the velocity of the fluid layer near the solid surface decreases to match the velocity of the surface, meaning it becomes zero if the solid surface is stationary. Moving further away from the solid boundary, the velocity of the fluid layers gradually increases until it matches the velocity of the main fluid flow. Due to the adhesion between fluid layers and between the fluid and the solid surface, the rotating disks are dragged along by the fluid flow and quickly gain speed. The most obvious advantage of using rotating disks instead of blades is that it eliminates turbulent flow, which reduces turbine efficiency, as previously analyzed. Even better, the absence of turbulence allows fluid particles to move smoothly within the layers of liquid. Each layer glides effortlessly past its adjacent layers without causing energy dissipation due to friction. Such flows are called laminar flow. It sounds like Tesla had created the perfect design, a revolutionary breakthrough for water and steam turbines. So why wasn't it widely adopted? Does the world have some kind of vendetta against this brilliant inventor? Not at all. In Tesla's era, the early 20th century, the efficiency of conventional blade turbines was very low. This was mainly because they relied on a direct drive system, meaning they did not use gear pairs to adjust speed ratios. This severely limited the maximum speed these turbines could achieve. At the time Tesla introduced his turbine, marine turbines were extremely inefficient. They often consisted of dozens or even hundreds of turbine stages, yet their efficiency remained very low due to their slow speeds. Take, for example, the turbine on the Titanic, which launched in 1912. It weighed over 400 tons, equivalent to 80 fully grown elephants, yet it operated at only 165 revolutions per minute, RPM. For comparison, the disks inside a Tesla turbine could spin at up to 35,000 revolutions per minute, RPM. Later, bladed turbines were equipped with gears, allowing them to operate at higher speeds. However, even with these improvements, traditional turbines still had lower efficiency than Tesla's design. Tesla claimed that the steam version of his disk turbines could achieve an astonishing efficiency of 95 to 98%. However, researchers estimated that the actual efficiency of the Tesla turbine was only slightly over 60%. In the 1950s, Professor Warren Rice attempted to recreate Tesla's experiments. A single-stage gas turbine, modified slightly from Tesla's patented design, achieved an efficiency of only around 36%. Even so, this was still an impressive result, considering that by 1939, the most advanced bladed turbines had not yet surpassed 20% efficiency. So why hasn't the world adopted Tesla's turbines? In a 1991 research paper, shortly before retiring, Professor Rice, whose last name means Gao in Vietnamese, analyzed the Tesla turbine using a laminar flow model to better understand its performance. More disks mean more surface imperfections and edge defects. These small irregularities disrupt the smoothness of the disks, causing the fluid flow to become less stable. As a result, laminar flow disappears, and the turbine's efficiency drops rapidly. Additionally, if the Tesla turbine is used to power heavy loads, such as a ship propulsion system, it would require a gear transmission system to distribute power to multiple shafts. This additional mechanical resistance would slow down the disks, further reducing the turbine's efficiency. In reality, the Tesla turbine's efficiency typically falls between 60 to 65%, which is only comparable to modern multi-stage bladed turbines. In fact, it performs worse than large steam and hydro turbines used in power plants, which can easily achieve over 90% efficiency. In conclusion, the Tesla disk turbine does not significantly outperform traditional bladed turbines, and in some cases, it is even inferior in terms of efficiency. One major advantage of the Tesla turbine is that it is easy to manufacture and inexpensive. If you disagree with this claim, feel free to explain why smooth disks would be more difficult and complex to produce than traditional blades. Another unique feature of the Tesla turbine is that it can rotate in both directions, something traditional bladed turbines, which are constrained to a fixed rotation direction, cannot do. Additionally, bladeless turbines work well with high-viscosity fluids, meaning substances that resist deformation, such as honey, molasses, molten chocolate, and certain types of engine oil. In contrast, water, milk, and fruit juices are examples of low-viscosity fluids. Since 1982, Tesla pumps based on disc turbines have been available on the market. These pumps are used for handling abrasive liquids, high-viscosity fluids, shear-sensitive materials, slurries containing solid particles, and other substances that are difficult to pump with conventional machines. Perhaps the most important reason why the Tesla turbine never became widely adopted is that Nikola Tesla was simply ahead of his time. He designed a machine that required materials his era could not provide. Even the best metallurgists of Tesla's time could not produce turbine discs that would remain perfectly flat and resist warping when spinning at 35,000 RPM. Warped discs create turbulent flow, rendering Tesla's design ineffective. Just look at a CD spinning at high speed, and you'll understand what Vifax was referring to. Unfortunately, by the time metallurgy had advanced enough to produce perfectly flat discs, bladed turbines had already dominated the industry for decades due to their continually improving efficiency. No one was willing to risk replacing them with unproven Tesla turbines. On the other hand, imagine a world where Tesla's disc turbine had been widely adopted from the very beginning. Who knows where 100 years of continuous refinement and technological advancements could have taken us? In conclusion, the world never rejected Tesla. He simply created a design that was too unique, too futuristic, and too ahead of its time for humanity to embrace.